GoToMeeting server went down and we couldn't get on, and I know you guys couldn't get on either for the webinar, but apologize for that. And using GoToMeeting for 3 years, that's the first issue we've had. So I guess we can feel lucky, but I guess 100% quality is better than 99 also. So let's get started. Our webinar session for this month is on root cause analysis. Root cause analysis is one of those very important proactive processes we need to do. We don't want to do too many of them, but again, when we have major problems or major issues, it's very important to understand the fundamentals of root cause analysis and how that can help us in the future being a little bit more proactive. We can see root cause analysis falls down on about halfway down our proactive curve. We can also see that RCM and failure modes effect analysis is the proactive way to do root cause analysis, and we'll talk about this more as we get toward the end of the session, because I think next month's topic is RCM and the fundamentals of RCM. But again, root cause analysis, very important to have this function or this process in our proactive area of our curve. So why do we do a root cause analysis? What are some of the main reasons? We're trying to prevent problems from reoccurring. So if we have major incidents or high cost incidents, we don't want those accidents or those incidents to reoccur. So root cause analysis, a lot of times, will keep them from reoccurring. We can reduce possible injury to personnel by solving some of those kind of problems. We can reduce rework and scrap many times. We'll show you an example of that from Whirlpool here in a few slides. You know, and if you eliminate a lot of these major failures, you're going to increase your competitive advantage. A lot of times it's to promote happy customers and stockholders with less issues, less quality problems. Ultimately, we're going to reduce costs and save some money by doing these processes where we actually find out what the root cause of the failure actually was. But a lot of times what I always tell people, look beyond the obvious. You know, invariably the root cause of a problem is not just the initial reaction or response. You know, when something happens and we automatically think we know why that happened, we go out and make that quick repair, we go out and make that quick adjustment. Sometimes we have to step back and look, what is the root cause of why this happened, not just the initial reaction or that initial response we have to the incident. And again, root cause analysis is just not restating what we find. It's an actual process that looks deeper into the situation. You know, it says here, often stated that root cause is quick but incorrect answer. For example, a normal response is equipment failure, human error. Now, the company I came from, we narrowed everything down that happened in the facility to 2 different factors, and we'll see those in a minute. You know, everything that happens, either some kind of an equipment failure or it's a human error that somebody happens, but that's just the overall lying problem. It's not the root cause. So the initial response is usually just a symptom. It's not the root cause of the problem. This is why a root cause analysis is a very useful and productive tool. So again, we're going to learn some techniques and of ways to do this. It says most of the time a root cause turns out to be much, much more than just that initial reaction. It could be a process or program failure that happened in the background. It could be a system or organizational failure that caused a problem. A lot of times we find it's poorly written work instructions is why we have human errors and a lack of training. Me and my son were doing a maintenance audit at a facility just a year ago, and the facility had not had any operator training or any maintenance training in 3 years. And they're having a lot of mechanical failures, a lot of problems. Well, a big part of the root cause was, operators not being up-to-date trained, maintenance people not being trained. So that became one of the root causes at this facility to help them get better and be more reliable. Again, when should I do a root cause? Well, a lot of times we have to make some boundaries of when we're going to actually sit down and do an official root cause analysis. Some significant or consequential events happen. A lot of times it's repetitive human errors occur during the specific process. Operators making errors over and over again. Sometimes we can find out from the root cause what those errors actually are. Another one, repetitive equipment failures associated with a specific process. A lot of times we can narrow down what those things are and what's actually causing those things to happen. A big one that we use, a lot of companies use for their root cause analysis is some safety or environmental incident. A lot of times safety and environmental incidents cost companies lots of money. And so again, that drives us to do the root cause analysis. A failure of a critical piece of equipment. You know, a gas turbine might be an example. If something like a gas turbine or a major piece of equipment fails, that may trigger a root cause analysis. A lot of companies I go to, they do root cause analysis based on a dollar loss. You know, there was one that any failure any downtime failure of $250,000 or equipment failure of $250,000, that called for an immediate root cause analysis. And then they had failures between 100 and 250 that, you know, they may make a decision to do a root cause analysis, but it's not immediate. And then anything under 100,000, they didn't do any root cause analysis. Now, those are big numbers, but it was a big company and a big process. But again, sometimes we have to set what is that major dollar cost that's going to trigger our root cause analysis process to kick into effect. This is one here, and I hope this doesn't offend anybody, but there was, you know, when I operated a plant a few years ago, or I was a manager of a plant, and we'd hired a new person in the refinery area of that plant. And over the course of about 3 months, he has 3 major incidents happen. You know, there was one where a rail car had got away, it rolled down the tracks, hit a derailleur, and rolled over into the woods and dumped a load of crude oil into the creek. And then there was a major fire on some insulation on one of the vessels, which burned off conduit, wiring, piping, and of course being down for 3 to 4 days to fix all that up and get the process happen again, major cost. You know, both these were over $250,000. And then there was another one during that period. So I called the supervisor into my office and was talking to him about these major incidents that were happening in his area. And this was one of his response. Well, he goes, you know, shit happens. And I go, no, that's unacceptable. It's unacceptable in a lot of industries. And the example I gave him, well, you know, does shit happen on an airliner at 30,000 feet? Well, if you're on that airplane at 30,000 feet, we don't want any mechanic in the airline industry having the attitude that, well, every once in a while something's going to happen. You know, if you live in a major city that has a nuclear power plant, would you want the people maintaining that process or maintaining the equipment to have any kind of an attitude that, well, every once in a while something's going to happen? And it doesn't. We have to have that same philosophy when we're operating our plants, that things just don't happen. There's a reason they happen. And if we can eliminate the reasons they happen, we don't have those major incidents. But a lot of times we have to do the root cause analysis to find out why. These industries here, you talk about the airline industry and nuclear industry, the reason they have very few failures is because they use the RCM process. And the RCM process defines these failures that can happen or have happened. And they develop maintenance strategies to make sure the failure never happens. So they do fewer root cause analysis. But if you take the airline industry, there's a root cause analysis done for nearly everything that happens on a plane. You know, if the plane lands and there's a rivet out of the wing or there's something wrong on that plane at all, you know, there's a root cause analysis done to find out why that happened, because they don't have those kind of incidents. If you look at this picture, here's an astronaut on the space shuttle. He's out there, and how many things can happen to this astronaut that can cause a major problem? You know, can he go out there and forget to hook up the tether that keeps him attached to the space shuttle? You know, can he drop a tool? You know, as he's going out here, can he snag his uniform or his outfit here and rip a hole in it? Well, none of those things can happen because they're going to lead to major failures of his life or the life of some of the equipment components he's working on. So he has to have things he does right every time. So this is a lot of times developing the right procedures and the right training so we don't have incidents that relate back to a root cause analysis later on. So whenever we have a root cause analysis, you know, there's some questions we need to ask. And you know, the first one is, why did the failure occur? And the question I always ask when I talk about this in my training is there one reason why a failure may occur? And most of the time there's multiple reasons. And a lot of times by eliminating one of those reasons, we can eliminate the failure from happening again. You know, if I ask the question, why did the Titanic sink? And I've asked this question in large groups, and you get multiple answers, 5 to 6 different reasons the Titanic actually sank. You know, the main one was it hit an iceberg, but, you know, what really caused it to sink? Well, if you look at this here, we had the Titanic sinking, but you can see here there was a number of reasons it sank. And there was an opening in the hull where the plates had buckled. Of course, the iceberg skimmed or hit, or the ship hit or skimmed an iceberg. But again, there had to be an iceberg present. You know, one of the main reasons the ship was in the water. If it wouldn't have been in the water, it would have never sank. But if you keep narrowing this down, it couldn't move quick enough. So, you know, late evasive action. They didn't have binoculars in there. They didn't see the iceberg early enough. And then the maneuverability of the ship, there were some engineering problems here where the rudder size wasn't big enough for that size ship. They had some cavitation in the engines. And again, as we all know from the data, they were going excessively fast, which gave them a little bit of less maneuvering capabilities. But again, if we would have eliminated almost any one of these things here, again, when we get into the plates buckling, the ship wasn't designed right to contain the water in that area and keep the ship from sinking. So again, if we would have eliminated any one of those items on here, there's a very high probability that the Titanic would not have sank. But again, it's finding out what was the real root cause, what could we have eliminated to keep this issue from happening again. But again, you can see here, here's a couple common ones. If you have a fire, you have to have three things. You have to have air, fuel, and an ignition source. And that's what we do in our fire programs. We eliminate one of these three things, we don't have fires. In our safety programs, as far as eliminating injuries, in order to have an injury, you have to have a person present. There has to be some exposed hazard that that person can come in contact with, and then they actually have to come in contact with it. So all your safety programs at a plant or a facility are designed around this concept of keeping people away from hazards, protecting hazards with guarding systems at your plant, and keeping people from going into and maybe not being in contact would be an example of an entry permit. You know, we make out an entry permit, we test the atmosphere, and we go through all the safety procedures to make sure if the person has to enter, you know, he doesn't come in contact with anything. So that's guarding and different things. So again, with good safety programs, you've eliminated one of these three things. So if we eliminate any one of these, the failure will not happen again or will not happen at all. So what are those basic elements of a root cause analysis? You know, what happened? What was the failure event, or what was the production loss that drove us to do the root cause analysis? How did it happen? What was that damage component? What was the error factor if it was on the human side? What actually happened here? Things we need to know in a root cause analysis. So why did it happen? We want to go all the way down to the root cause level. Sometimes you can get down there and find out it's multiple things, but we have to pick out one that we can eliminate to keep the failure from reoccurring. Now, how are these elements determined in a root cause analysis? So we'll look at a couple examples here. So if we look at this one, and this is very similar to the company I came from, where we said there's only two reasons that we have failures, we have incidents. The first one is that mechanical. Well, the first one here we see in the yellow is the human factor. So why do we have human failures? These are behavior factors or human errors. They're based on knowledge, rules, skill-based, judgment of the human, execution, compliance errors that result in incorrect activity. You know, which one of these things actually caused that human to make that mistake? And again, do we train the person right? Did we train him to use the right judgment? But here's a couple examples below this of why it happened. It says the person couldn't, but it says the person wants to perform his role, but needs training, may need knowledge, may need some better written procedures, may needs guidelines, maybe needs some tools to make him more aware so that they can actually perform the job. Because in most cases, most people in plants, the majority of people in plants, they want to perform their job correctly. They want to perform their job right. But we have to give them some of those things to do that. And then in a few instances, you have these where the person knowingly violates a policy, violates a procedure, takes a shortcut, and you have an incident. So how do you control these two things? How do you control people knowingly violating policies? You know, do you have the right disciplinary actions in place? You know, one of the things I notice when I go do training in the mining industry, you know, one of the rules in the mining industry is no one can ever get on a piece of mobile equipment. The very first thing you have to do is fasten your seatbelt. I don't care if it's a pickup truck or a big mining piece of equipment, a bobcat. And in that industry, in the United States and especially in Australia, if you get caught with a piece of equipment in gear or started without your safety belt on, it's automatic termination. So again, they've taken all the discussion and the thought process out of a safety policy that has caused them death and injuries in the past. So now we get over to the next slide here, and it says these are the mechanical failures. These are tangible factors. It says failures of components due to corrosion, erosion, fatigue, overload, or thermal mechanisms. These are the main things that cause mechanical failures. So why would that happen? Well, in the first example here, it says the design was wrong for the application. Now, some people say, well, that's probably not very common, but that's more common in the industry than anybody wants to admit. Many industries have done studies on this. We did a lot of these at the company I work with. And we buy equipment originally based on the cheapest price and not the correct design. So there's a lot more of that out there than people realize, where the design's wrong for the application. Here's one here. Why did it happen? Servicing the component was not properly maintained. Now, what does that mean? That means maybe we're not doing the PMs correctly. Maybe we're not doing PMs on the correct interval. Maybe we're not doing PDMs. So there's a lot of things that goes into servicing that component and properly maintaining it that will cause the component to fail at an earlier stage. The third one down here, maybe the operation of the component was operated beyond its design limits. So are we operating some of the equipment? Now, this was very common in the industry I came from. I worked for one of the largest privately owned companies in the world. And one of the things that we did, or the company did quite often, that we had to follow suit with, was you would build a plant that was designed for a certain rate per hour, rate per day. And after that plant ran for a year and a half, they wanted to add 15 or 20% to the rate. So we'd speed things up, add a little bit of equipment. Well, most of the facilities in that company ran at 50 to 100% over what they were designed to do. We operated beyond their design limits. And again, maintenance cost was going up. Failure numbers were going up because we were doing that. Yes, we were getting more rate out of the equipment, but lots of equipment wear and lots of equipment downtime. So we operated beyond its design limits. Here's a simple root cause analysis where they have a pump failure, and they list three components of the pump: the motor, the coupling, and the pump. So what failed in the two components of the pump? You have an impeller and a bearing. The bearing failed. Down below the bearing, there's a number of reasons why a bearing can fail: poor design, contamination, wrong lubricant, dirt contamination, degraded lubricant, misalignment, incorrect installation. Well, it turned out to be dirt contamination. Well, how would that happen? Well, they ended up having a filter failure. And the filter failure, the filter not only wasn't full, or the filter didn't fail, the filter was full. Why was it full? Well, the differential pressure gauge had failed and plugged, and they didn't know the filter was full, which ended up being the root cause of a bearing failing. So again, a root cause analysis process used at a company here to define this bearing failure. But again, we covered these three things. What's the failure event, the damage component? What's the error factor? Well, remember this: the root cause of all failures and events are inadequate systems to prevent errors and defect. Now, these inadequate systems could be people issues, lack of training, lack of procedures, which could be a system. They could be improper maintenance, wrong maintenance intervals, wrong maintenance techniques. So a lot of things go into inadequate systems to prevent failures and defects. But that's what you want to look back at. What am I doing? Am I doing the right thing to keep these components from failing? So why do a root cause analysis? It says just fix it. There's just too much to do. Now, this is a comment you hear in a plant where, we're way too busy. Let's just get it fixed, get it back up and running without trying to find out what the root cause. Somebody told me this: we don't even have time to think. We just need results now. So we don't have time to do this thing called root cause analysis. But again, in reality, you're fixing symptoms without regard to the actual cause. So a lot of times that's what we do in our maintenance process. We just fix the symptom. We do something to cover up what the symptom might be. But the root cause analysis is a structured and thorough review of the problem designed to identify and verify what is causing the symptoms. So this is what a really root cause is: looking at all the symptoms and getting down to the root cause of the failure, root cause of the incident. So some different definitions we'll see in a root cause. The cause is just a causal factor. It's a condition or event that results in some effect. The direct cause is a cause that directly resulted in the occurrence. And this is a lot of times what you'll find out when you get toward the end of your root cause analysis. Then they have one called a contributing cause. This is a cause that contributed to the occurrence, but by itself would not have caused the occurrence. So this is a side factor, and sometimes you'll catch yourself in a root cause going after some contributing cause. And the root cause, if corrected, would prevent the reoccurrence of this incident and similar occurrences. So again, some different definition of words you can use when you're doing your root cause analysis. So how a root cause analysis is done? Well, teams identify all the possible causes. And one of the things we like to point out, we like to do at my company, is you don't just want one person to do the root cause analysis. You have to have root cause analysis teams where you get people in there that understand the process, people in there that will understand what the failure actually was, people in there that can understand how to correct the problem after maybe you found out what the root cause is. So root cause analysis is definitely a team effort. Making sure the actual root causes are identified and verified. And then this is one. I have a lot of companies that I've been to where they're doing root cause analysis. When I do a maintenance audit, I always ask for the information or ask for some backup material. They've done the root cause analysis, but there's no information there to say that they've ever done anything with the corrective action. So we need to, whenever we figure out what the problem is, we have to have some corrective action that takes place to let us or to guide us to go out and eliminate the problem. So I get this all the time. Well, corporate wants us to do so many root cause analysis a month or so many root cause analysis a year. Well, that's just a corporate initiative to make sure root cause is being done. But if there's not a corrective action being done at the end, the root cause analysis process is probably not going to do you much good. So relationships between cause and effect. You know, this here is the reason for the team effort. Need for creative thought to identify all the possible causes. Don't jump to conclusion on what the cause is. This is one that I catch companies doing all the time. Collect data about the problem. There's always facts and information you can go out and get in the field. You know, maybe what was the pressure at the time it happened? What was the temperature at the time this happened? What other factors may have been happening? Is there data in the CMMS system? Is there data that operators collected that we can use or wrote down that we can use in solving the problem? And then how are you going to analyze that data? You know, sometimes if it's a major problem, we need to take a little bit of time to analyze the data we have and make sure it's good data, make sure the data relates to the problem. And then how do you verify the causes? You're going to end up with multiple causes, just like the Titanic sinking. How are you going to verify those causes? A lot of times we can do that with data. Instead of just going into a room and talking about what happened, make sure if it's some that you can get data on. And the data may be just interviews with operators, maybe interviews with, or maybe just asking questions. And again, maybe there is data in your CMMS system or some recorded data that you can use. But different kinds of root cause analysis tools. You have cause and effect diagrams. We'll look at some of those. You have scatter diagrams. You have control charts that may be used. They have a process we're going to talk about here called 5 whys. And this is something that's pretty simple. I have one of my customers, they just take the sticky notes, and they'll take yellow sticky notes, and they just keep asking why 5 times. On the 5th or 6th why, they change that yellow sticky note to a red one. And a lot of times that gets you down to one of those root causes that you can eliminate and eliminate the problem. There's tree diagrams, there's change analysis, there's barrier analysis. We don't have time to go over all these today. There's event and casual factor analysis. There's management oversize and risk tree analysis. So you can see there's a number of different methods different companies around the world use to do their root cause analysis. But again, most of these you're gathering data, you're putting some data together. Here's an important fact. You know, a cause effect, it's a visual display of possible causes. And this is one of the things in a root cause analysis that I'm just talking about it. There's a lot of root cause analysis software programs, a lot of information out there, but getting the information up so we can visually see it, writing it on whiteboards, writing it on flip charts. You know, what are the cause categories? Materials, machines, methods, and people. We'll look at a couple cause effect diagrams here in a minute where we can actually list these things separately. And this reveals gaps in what we have in our existing knowledge. It's a great learning tool also. You know, it helps teams reach a common understanding of why the loss exists. So again, visual data, very important, you know, in a root cause analysis. So here's a cause and effect diagram. So we have this problem off here to the right. So we have, was there any procedure problems? Was there any people-related, human-related problems that went along with this? Was there any equipment type problems? Was there any materials issues? And again, on each part of this cause and effect diagram, we can list things underneath each one of these that may track down where the real problem is, where the root cause is. So if we look at this one, we have a problem here. It says cannot load software on the PC. So it says here, our first one in methods, that they put the CD in upside down where the instruction's wrong. Was there any human errors? Cannot answer prompt question. Was there brain failure? There's some common ones here. Materials. Was there a power interruption? Was it a bad CD? Was the CD missing? Was it a wrong type of CD? In your machinery, maybe there wasn't enough memory. Inadequate system, graphics card incompatible, hard disk crashed. So again, you can see here they used the cause and effect diagram and they just started listing potential issues that could have related to not being able to download the software. The same thing you can do here with any problem you have in your plant. Nice, easy diagram. You can draw this on a whiteboard. You can draw this on an easel pad and just start filling in the blanks. Put your problem off to the side and fill in these areas. So the danger of the cause and effect diagram, it's a list of potential root causes, which includes both probable causes, real causes, and guesses. Now we have to do something with this information, right? Because you can see from the last one we looked at here, lots of information here. What's highly probable? What can we use from this information? So now we have to go back here and select things that are probable and we could actually work on. So it says here, after the cause effect diagram, identify likely candidates for root cause by one of the following actions. It says look for causes that appear repeatedly within a major or across a major cause or process category. It says look for changes or other sorts of variation in the process or environment. Use consensus. Again, this is a team making decision, so use some consensus in this decision making process to select the right root cause that you may want to go after. And then it says here, collect data to confirm the potential root cause. Don't jump to assumptions. This is it. This is what we got to solve. Is there a way to collect some data to prove that this is a potential root cause or this is a potential issue for this process or this incident that may have happened? Now we've got another one called 5 Whys. Again, I've got a lot of companies I see using this. They use it very simply. A lot of them, they use it too fast. But I put some specific slides in here on this. If anybody wants, there's a PowerPoint presentation that I got from a company that goes into more detail on 5 Whys. But again, 5 Whys is a simple process. Describes the problem in specific terms. It says for each likely cause, ask the question, why did this happen? And just keep going down. Continue for a minimum of 5 times. There's lots of times when one of my customers, they say, well, I get to the 4th why. The group decides that's the answer. Sometimes you have to go to the 6th why to get to a different root cause. It says show logical relationship of each response to the one that preceded it. Now, I've been in 5 Whys where you have maybe a human incident and a process or mechanical issue, and you have 2 trees of your 5 Whys. You're going to ask 5 times down both those trees, the human and mechanical area, trying to get to a root cause that you can actually get data or possibly eliminate. It says stop the team, or stop when the team has enough information to identify the root cause. That's what I mean. Sometimes you'll get there in 4 Whys by asking the question why 4 times. Other times it may take 6, but somebody in the group has to stop it at some point where you think you have a root cause that you can actually eliminate. So here's an example of a tree diagram. Again, much like the cause effect, but state the problem. Causes are listed as branches to the right of the problem. So it's like a tree. It says continue to clarify the causes, drawing additional branches to the right. Repeat until each branch reaches its logical end. So very, very much like a cause and effect diagram. So here would be an example of a tree diagram. So our example here says the training class is canceled. Why was it canceled? Well, there's 4 possible reasons here. We don't know what the end is yet, but not enough students signed up. It was canceled because the trainer was not prepared. Materials not completed. or the training department had other projects they had to work on. So again, why would there not be enough students? Too much work, no reward, schedule not communicated. That could be an answer. Your trainer not prepared. A new trainer was assigned too late, no lead time, turnover maybe. But again, you can see this is an example of a tree diagram, kind of similar to the cause and effect diagram, but you're listing all these possible reasons why this class was canceled. Same thing you can do with a problem in your plan. Easy to do on a whiteboard or an easel pad, and also easy to do with sticky notes. Cautionary note, and this is one. This is a quote from Albert Einstein, and this is one you want to remember. It's impossible to solve significant problems using the same level of knowledge that created the problem. And what this means is there's a guy I know in the industry. His name is Mark Galley. Mark Galley is probably one of the leading root cause analysis experts in the country and in the world. He was called in when the space shuttle blew up. He was called in for a number of major incidents that happened around different industries. You know, the BP oil spill, the BP Texas City explosion. Mark Galley is very good at this, and so sometimes we have to increase the level of knowledge in our root cause analysis team. So that may be involved sometime in, if it's a major equipment failure, bring in the equipment vendor. You know, if it's a human error problem, you might want to bring in the training group or your HR group. But again, you can't solve the problem with the same level of knowledge that created the problem. So again, don't be afraid to ask for more expert help. Here's a cautionary note on the cause and effect analysis. You can't get past existing knowledge. Must have either observed or considered that the cause produced the effect in the past. Where's the information coming from? So again, here, why not just ask why? So this is a systematic approach. You need to systematically organize and analyze the data. First, understand what happened and then why. There's typically multiple root causes, as we saw on the Titanic sinking. You know, blame is an obstacle. You don't want to blame anyone for any specific instance. And again, when you're doing root cause analysis, or especially like in TPM, we don't want to have a blame factor involved. We're not out looking for somebody to blame the problem on. You know, guides need to investigate human performance problems. How do we do that? You know, where does the blame go when we have human issues we're trying to solve? You need to ask the right questions to completely understand why. You know, some root cause analysis techniques may provide easy answers that are either incompatible or wrong, but easy to find. So again, trying to dig up and get the right information. So let's do a little overview of 5 whys. It says 5 whys is a root cause analysis tool, not a problem-solving technique. The outcome of a 5 whys analysis is one or several causes that ultimately identify the reason why a problem was originated. There are other similar tools, as the one mentioned below, you can be used simultaneously with 5 whys to enhance the thought process and analysis. So what is the problem? What is the root cause? And then again, always remember this. What is the corrective action? It's not just finding the root cause, but how are we going to correct it? How are we going to eliminate it? So it says any 5 whys must address 2 different problems at the same time. You know, the first part is related to the process that made the defective part. Why was it made? Why was it defective? The second part is the detection system that was not able to detect the defective part before it became a problem. So it says here the lack of detection of a defective product excuse me, is a problem of its own and must be treated independently than the product problem itself. So just by knowing you have a defective product is not good enough. Why did it happen, and why didn't we detect it before it became a problem? It says even though the discipline is called 5 whys, it's not always necessary to reach 5 before the root cause of a problem is fully explained. Or in some cases, it may take more than 5 whys to get to the bottom of the problem. It will depend on the complexity of the process and the problem itself. It says in any case, 5 has been determined as a rule of thumb as the number at which most root causes are clearly identified. Do not worry about not meeting or exceeding this number. Just follow your thought process and let it decide how many whys you require to get to the point where the root cause is evident and can be eliminated. It says ask the full question, including the problem or the cause behind it. If there is a problem with labeling, ask why was the part labeled incorrectly? If the answer is unreliable database, ask why is the database unreliable? It says if we do not follow this approach to answers, the whys tend to lose focus on the third or fourth why. So it said that a well-defined problem is half resolved problem. Hence, it's important to state the problem as clearly as possible. It states here, whenever possible, define the problem in terms of requirements that are not being met. This will add a reference to the condition that should be and is not. So the first why, very important. A clear statement of the reason for the defect or the failure to occur, understood even by people that is familiar with the operation where the problem took place. So again, clearly state the problem. It says often the first why must be short, concise, state a sentence, that plainly explains the reason. Do not try to justify it. There will be time to do that later in the following if it's pertinent to the thought process. It's okay to write it down even if it seems too obvious for you. It may not seem that obvious to other persons that read the document. So while you're stating this problem, if you got other ideas, make notes of those because they're going to come up later. The second why, it's a more concise explanation to support the first statement. It says get into the technical arena. The explanation can branch into different root causes here, so it's okay to follow each of them, continuing with their own set of remaining three whys and so on. So again, this is where you might get into that second why, and there could be a human factor you want to follow, or a human error. There could be a mechanical failure or a mechanical error you want to follow. So this is where your 5 why could branch into 3 more questions on each side. It says on the third why, don't jump to conclusions yet. Follow the regular thought process, even though some underlying root causes may start surfacing already. It says this third why is critical for the successful transition between the obvious and the not so obvious. The first why you've prepared, you focus on the area where the problem could have been originated. And the last 3 whys is why you take deeper into comprehension of the problem. Visualize the process where the product went through the process mapping and narrow it down to the most likely sources of the problem to occur. It says you do not need to answer all the whys at the same time, which means follow your human error, follow your mechanical error down. The fourth why. It says clear your mind from the preconceived explanation and start the fourth why with a candid approach. You may have 2 or more different avenues to explore now. Explore them all. Even if 1 or several of them turn out to be not the root cause of the problem, may lead to continuous improvements. This is a good time to include cause and effect analysis and look at the 5 M's. Is there an issue with method, materials, manning, machines, and Mother Nature? Again, this comes up in some cause and effect training, that these 5 M's, what may have caused the problem. Most of the time it's not Mother Nature, it's one of these other 4 M's, but again, always questions to ask. It says, finally, now we get to the 5th why, and it's likely you have found a systematic cause. Most of the problems in the process can be traced to them. Even a malfunctioning machine can sometimes be caused by incorrectly followed preventive or incorrect machine parameter setup. When you address a systematic cause, do it across the entire process and detect errors that may be under the same situation, even if there's no reported issues yet. If you have reached the 5th why and you're still not dealing with process-related causes, you may still need to do 1 or 2 more whys to dive deep into the systematic cause. So again, just keep asking why that happened. So I say a good way to identify 5 ways it was done properly is to try to organize and collect data into 1 sentence and define it in an understandable manner. If this cannot be done or the sentence is fragmented or meaningless, chances are there's a gap between 1 or several of the whys. You must then revisit the 5 why and identify those gaps and fill them in. If there's coherence or a way to sentence is assembled, it shows consistency in thought process. Something like problem description occurred due to the 5th why. This was caused by the 4th why, mainly because the 3rd why was allowed by the 2nd why led to the 1st why. So again, it sounds like it's getting difficult here, but 5 why is actually pretty easy if you just keep asking, why did that happen? In 5Y, it says, don't forget that the sought outcome of 5Y exercise is the root cause of a defined problem, not the resolution of the problem itself. That'll come later. 5Ys is a standalone problem-solving technique, but more of a tool to aid in the process. It says, do not worry about the action plans of effectiveness verification yet, as will be addressed later. Focus more on identifying the reason that allowed the problem to happen and escape. If you come up with a reasonable answer, the 5Y exercise would be successful. If it cannot be done, then quite probably the more data needs to be collected if a better grip of the problem, and the 5Y process can then be restarted. And I've had this happen in RCMs. You get to a point where you're asking these questions and there's not enough data in your group. You haven't went out and gathered enough data to be able to answer the next why. So you may have to go back and get some data and then restart your 5Y. One final point to ponder. A problem that cannot be reproduced is a problem that hasn't been resolved yet. So it says, challenge the root cause that resulted from the 5Y exercise to try to reproduce the defect. If you cannot, there's a very big chance that you've not gotten to the bottom of it yet. If you not reproduce them, move on to the corrective action part and congregate your team for a job well done, or congratulate your team for a job well done. But again, we have to be able to reproduce the problem somehow in order to get the answer. But here's a company, we couldn't put the company data in, but this is a process area downtime for this company. So they had, these are in minutes, I think, but 845, or 858, 845, 296, and after the root cause, they drove process area downtime to 0. Here was an example of monthly production losses in dollars. And you can see they had one at 700,000, one at 300,000, one at 600,000. They did their root cause analysis and they drove these monthly production losses down near 0. This was a pump repair cost for a company. They were keeping track of pump repair cost. And look what happens. They do their failure analysis complete, solution implemented. They drove their pump repair cost to 0. This is some information I just stuck in your slide material, some good information for root cause analysis coding categories, but it breaks the root cause analysis down into equipment and material problems, procedure issues, personnel problems, design problems. And again, this training deficiency, very big one. If you're not doing a lot of training at your facilities, you're going to have some of these. Management problems. None of us have any management problems, but a good category to look at once in a while. And then external phenomena, such as weather, power failures, and things like that. So again, just some extra information I stuck in your root cause analysis information here. Here was Whirlpool. In this Whirlpool plant, they experienced 8 equipment failures, spent $43,200 in labor and materials to repair. They invested $16,000 in 2 failures, drove the entire facility in unplanned shutdown. The 2 failures occurred within 30 days of each other. They constructed a root cause analysis team. They found 8 root causes, 4 human errors, 3 latent errors, and 1 equipment root. They enlisted the help of equipment vendors. They improved reliability of machinery, and then when they tabulated the total cost, they'd saved $96,000 when maintenance, labor, scrap, and lost production costs were tabulated. Again, this is another thing I always tell people to do with their predictive programs. Put a dollar cost behind your fines. If you do a root cause analysis, write a little report, put a dollar cost behind what the company saved or what the payback is for doing the root cause analysis. Here's Alabama Power Company. They had a pump that failed 5 times in 6 months. They developed a root cause analysis team, and they found out that they replaced the failed pump bearing with the wrong type of bearing. And it was in their CMMS system, only listed 1 type of bearing for the failed unit. It didn't specify the replacement was to be the inboard bearing. So again, they figured this out, but 5 pump fails 5 times in 6 months, that's a major issue. But again, root cause analysis, use some kind of RCA, even if it's just a why discussion. And like I say, I started companies off that weren't doing any. We just take the yellow sticky notes. We ask why 5 times. On the sticky notes, on the 5th why, we change that to one of the pink or red sticky notes, and we go out and try to solve that problem. But again, root cause analysis looks at failures after they've occurred and how to prevent them from happening again. RCM, failure mode effect analysis, looks at failure modes before they occur, and we look at ways to predict, prevent, or eliminate those failures. So it says here you should be doing some of both to move to this higher plant efficiency. So again, if you're doing too many root cause analysis, that should be a sign that you have some issues. So be proactive. Start doing some more RCM. Start doing some more failure mode effect analysis. One of the processes we're going to do in next year's webinar after January is we're going to do some failure mode effect analysis training. I've got a spreadsheet that I'll actually give you after that webinar next year, where you can do your own failure mode effect analysis. But with the 1 hour training we'll do online at the webinar, you're going to understand how to do failure mode effect. We'll actually do a small one online. So that's one of the webinars you'll want to make sure you sign up for next year. So again, see where RCM or see where RCA is at. It's on the proactive part, but actually if you look down the lower right-hand corner, we're all going to do our root cause analysis after the failure. But we have to find ways to be proactive. Do a failure mode effect analysis on your critical equipment. Do an RCM analysis. We have RCM software available, which we'll talk about next month and next month's webinar training. I'll show you a couple RCM software packages that we offer where you can very simply do RCM at your own facilities with your own people. Most of your RCM processes are very expensive. You're talking $18,000 to $20,000 for the software, and then licensing agreement. Our software packages are very cheap, and there's no license agreement. We can teach you how to do RCM right online. But again, always remember this: root cause analysis is done after the failure. RCM, failure mode effect analysis, is done before the failure occurs. This is why the nuclear industry, the airline industry, the military have very few mechanical failures, because they do the processes before the failure occurs. But again, one of the biggest failures I find in root cause analysis is, and in RCM, is we do these processes and we don't implement our findings. So one of the key things we need to do when we do an RCA, we do an RCM, is go out and implement what you found, correct what you find. It says don't do the process because it's required by corporate. Don't do it because it'll make your process more reliable, or do it because it'll make your processes more reliable, and you'll have less of these major failures and major incidents. Very important process, but we have to implement the findings. All right, so that concludes our webinar for today. Justin will actually send you, we'll have the recording available for download. And again, I apologize for Tuesday. We didn't get very many people on the call today, but we'll send an email out and we'll send that to you. We'll also send you a PDF of the slides today. So I hope you enjoyed the presentation. Hope we don't have any GoToMeeting issues next month. So we'll look forward to seeing you next month with another session. Thanks for joining today.